What kind of mathematical statement could remain unsolved for over 350 years, despite the best efforts of the world's greatest minds? This is the story of Fermat's last theorem, a single line in the margin that became one of the most famous puzzles in the history of mathematics. Pierre de Fermat wasn't a full-time mathematician. He was a 17th century French lawyer and magistrate based in Toulouse. Yet in his spare time, he made profound contributions to mathematics, especially in number theory, probability, and geometry. While reading a copy of Diophantus's Arithmetica, Fermat scribbled a note in the margin beside a particular problem. It read, "I have discovered a truly marvelous proof of this proposition, but this margin is too narrow to contain it." He was referring to the equation x to the power of n plus y to the power of n equals z to the power of n, claiming that there are no positive integer solutions for n greater than 2. That single cryptic note would go on to puzzle mathematicians for more than 3 centuries. Strictly speaking, a statement isn't a theorem until it's proven. Fermat's claim had no known proof, at least none that he shared. Yet over time, it came to be known as Fermat's last theorem. Why? Because it was the last of Fermat's major conjectures to remain unproven. And despite the lack of a formal proof, the mathematical community adopted the name, partly out of tradition and partly because of Fermat's remarkable track record. Many of Fermat's other marginal notes, such as Fermat's little theorem and his result on sums of 2 squares, were eventually proven by later mathematicians like Euler. This history gave his last theorem an air of credibility. Mathematicians believed it was likely true, even if no one could prove it. Yet, in the early 19th century, Sophie Germain, a pioneering French mathematician, made substantial progress on Fermat's last theorem. Denied formal education, she studied under a male pseudonym and corresponded with great minds like Gauss. Germain developed what is now known as Sophie Germain's theorem, which dealt with the first case of Fermat's last theorem, where the exponent p is a prime that does not divide any of the integers x, y, or z. She showed that if both p and 2p or plus 1 are prime, then certain types of solutions are impossible. Although she couldn't prove the theorem entirely, her work provided a critical foundation and influenced later mathematicians. Fermat's last theorem was sometimes nicknamed the Lady's Theorem in honor of her remarkable efforts. Fermat's last theorem wasn't just a historical curiosity, it became one of the great driving forces of modern number theory. In the attempt to prove it, mathematicians developed powerful tools in algebraic number theory, modular forms, and elliptic curves. Then in 1994, after working in secret for years, British mathematician Andrew Wiles finally proved the theorem. His proof used ideas far beyond anything Fermat could have imagined, including the deep connection between elliptic curves and modular forms known as the Taniyama-Shimura-Weil conjecture. Wiles didn't just close a chapter, he opened an entirely new one for mathematics. Fermat's last theorem reminds us that even a brief margin note can spark centuries of discovery. Its story is one of persistence, creativity, and collaboration across generations. Sometimes it's not just about solving a problem, it's about everything we discover in the process. Thanks for joining me on this journey through one of mathematics' greatest legends. If you enjoyed this story, do like, share, and subscribe. And remember, behind every scribble, there might just be a revolution waiting to happen.